Hi and welcome back to another video in the series covering dynamic simulation. In this video we are taking a look at a simulation of a baseball flying through air on a two-dimensional trajectory, also taking into account air resistance. The simulation coming out at the end simulates the trajectory of a baseball flying through air like you see on screen right now. We start by taking a brief look at the equations required to mathematically describe the dynamic movements. Afterwards, we reformulate those equations to the form that our numerical integrator requires. Then we cover some details in the implementation, which are specific to this example, and I show you how you can automatically detect when the baseball hits the ground in simulation to stop the simulation precisely at that point. Afterwards, we briefly analyze the simulation results and attempt to validate our simulation. The first sections of this video are kept a lot shorter than in the last video, because I left theory out of this one that has been covered in the previous video, so we can focus on some new topics. If you need a refresher on some of the theory, or a part is covered with too little explanation, best watch the previous video next. All the code for this and the previous simulation example can be found in the links provided in the video description. There are a couple of forces acting on our baseball. Gravity, a force resulting from air resistance, which can be split up into its x and y components, and the effects of inertia. I know it looks kind of weird drawing all forces into the positive direction and then writing the equations with the minuses. I personally am used to doing it like this and I make less mistakes this way. I hope it's not too confusing to look at. Our baseball has a diameter of 74 millimeters, about 3 inches, and a weight of 142 grams, about 5 ounces. Written everything down into SI units, so in meters and kilograms that we have to use for the simulation. The air resistance can be calculated with the equation shown here, where the parts are the surface area of the baseball calculated from the diameter, the density of air on ground level, assumed to be constant here because our players will not hit the ball up into the stratosphere, a factor describing the shape, where we just take the factor of a sphere, and the velocity of the baseball squared. Since the relationship between velocity and air resistance is non-linear, we first have to calculate our tangential velocity, calculated from the individual velocities in x and y directions like this, simplify once, and then use that to calculate the total air resistance. At the end we must use the angle and sine and cosine to split it up into its x and y components. Our next force acting on the baseball is the gravity pulling it down, calculated from the mass of the ball and gravity. The acceleration in x and y direction lead to the forces of inertia as shown, and summing everything together allows us to calculate the acceleration in x and y direction that we need for our simulation. Writing it down as a state space model, which was covered in greater detail in the previous video, results in the state with the 4 entries, position and velocity in x and y respectively, where y is our height over ground. In order to show you some more details when it comes to implementation, we will start our baseball at a height of -10 meters and stop the simulation when we hit -5 meters. This comes down to a terrain looking like this. If you want to have it start at 0 and end at 0, you can just remove some of the extra steps. But I figured I include those because that way you can learn more. The code consists of the following 3 parts. Our main function, or main script however you want to call it, the function describing the differential equations of our system, and a function that is used by our integrator to detect when the baseball hits the ground to stop the simulation automatically. This third part is something new in this video and I will talk about it once we get there. I also found a way to have nicer looking code in this video. I hope you can appreciate the new look. We start by going through the main program. First we clear everything and do some housekeeping for the plots. If you uncomment this section here, you can create a folder automatically to save the simulation results. This works on Windows. I am not sure about other operating systems, that's why I decided to comment it out in the code provided. Afterwards, we create a structure for our simulation parameters and set up the start values. We set the velocities at the start to be equal to our initial velocity when taking the launch angle into account, because the baseball should fly off into the desired direction. And we set the starting height to be equal to -10 meters. Up to now, those parts are identical to the previous video. As you can see here, we now define an additional options structure with event handling. This is used to detect when our baseball hits the end point by detecting when the sign of a variable changes from being positive to negative. This options structure is then passed to the integrator as the fourth input, as you can see here. Well, the first parts are the mandatory inputs that you know from the previous video already. Our simulation model, the time span, and the start values. Let me just bring the system state back up on screen here for reference, and let's check out our two functions. We start with the event handling function, where we have two mandatory inputs in our standard configuration, the simulation time and state, and as many additional inputs like we do here, where we pass the structure containing the simulation parameters in as well. The function has to return three outputs. To handle a single event, like in our case, we provide single outputs. If you provide vectors, you can detect multiple different events. The outputs required are, first, the state, where we want to detect our zero crossing. In this case, when we cross the height of -5 meters, because that is what we defined as our endpoint, and this is the event we want to detect. Second, a Boolean variable to say if we want to stop our simulation there or not. It can make sense to use event handling to just detect zero crossings without stopping the simulation. Maybe I make a video covering this in the future. If I do, I will link it in the video description below this video. And third, we can set an option if we want the direction to matter as well. The way it is set up here, we only hold our simulation if we cross 0 from the top. Setting this value to +1, we trigger the event when we pass into the positive direction, 0 if the direction does not matter, and -1 if we want to detect it in the negative direction, like we do here. This way, the baseball can cross the -5 meter line at the start without stopping the simulation, but the simulation actually stops once we reach this point here. This is already it for the event handling. Implementing and using it like this will ensure that our simulation stops precisely at the defined endpoint, precisely down to a certain tolerance that is. We can now continue with the second function, the function where we implement our system equations. We again have to provide our mandatory in and outputs, the time, system state, and the change of state as output, and our third additional input that we provide where we pass the parameters in. For the code, we first add our documentation like last time, continue by dividing the state into individual variables so everything is easier to read. As mentioned before, since we have nonlinear system dynamics, we must calculate our total air resistance from the tangential velocity, as you see here with the equation shown previously. Next, we determine the angle of our air resistance force with the arcus tangens 2 function, where the sign of the velocity in x and y are taken into consideration automatically, so we do not have to worry about the quadrants. I have added an option here where you can switch to use the regular arcus tangens function over the arcus tangens 2, which leads to an incorrect result in the simulation, and we take a look at what happens if you do so later in the video. Next, we calculate the x and y components of our air resistance force and the gravitational force with the equations shown previously, right here. In the last step, we calculate the acceleration and pass them back with our change of state vector. Now we are done with the function and continue with the main program. Like last time, we call the integrator, use this block down here to reconstruct our acceleration after the simulation, and can get to plotting of the results. In the last step, we plot the results. plot lines for our ground, add a legend, axis labels and the title. The title is set up in a way that we plot our final position and the total time of flight as well, and so on. Taking a look at the simulation results, here the position in x and y, we can see that our baseball travels along the expected trajectory. We can also see that the simulation stopped at the timestamp shown in the title of the plot when our event of hitting the ground got triggered. Even though we set the simulation time to 100 seconds, as you can see if we bring the line calling the integrator shown previously back on screen, the simulation stops as soon as we are hitting the ground with a certain accuracy. A different visualization of our simulation results is shown here, where the velocity and acceleration in x and y direction over time are plotted. Here we can see the influence of air resistance. At the start, when the baseball is still flying up into the air, our negative acceleration is bigger than gravity. This makes sense because we have gravity pulling down and the air resistance holding against the ball as well. But as the velocity in our vertical direction changes from positive to negative, when our baseball changes from going up to going back down, we can see that the acceleration becomes lower than that, because now the air resistance acts against gravity. In an attempt to validate our simulation, we now run a few more analyses. The analyses here are aimed at figuring out if we made any easy-to-catch implementation mistakes. For our first analysis, we launch from height equal to 0 and stop once we reach height equals 0 again. We sweep our initial launch angle from 0 radians to pi half, so 90 degrees, launch all of our baseballs with a defined velocity at different angles, and record the trajectories to figure out how far we managed to fling our baseballs. The calculation for this was finished rather quickly, creating the animation was not. Let's remove this animation from screen and plot the distance depending on the initial angle. I have converted the angles to degrees for this plot because I think that makes it easier to read than radians. As we can see, the maximum distance is reached if we launch our baseball at an angle of around 42.7 degrees. It is not an angle of 45 degrees because of the influence of air resistance. We will take a look at another animation showing this in just a moment. Let's look at the second plot first. Here we can see a comparison of tangential velocity of our baseball, and we compare the initial velocity to the final velocity, again for our different starting angles. Since our terminal point is on the same height as our starting point, and since we are taking air resistance into account, our final velocity must be lower than our starting velocity, which is the case as you can see here. If this would not be the case, we would know that something is not quite right in our simulation, but it looks correct to me. Let's now bring back the animation shown previously and mark the trajectories for our launch angle with maximum distance and also the angle launched at 45 degrees. We can now zoom in, launch all the balls again, and follow our ball launched at 42.7 degrees. The second one, marked up here, is the ball launched at 45 degrees. We can see that right at the end the two paths cross and the baseball launched at 45 degrees actually comes in a little bit shorter. This is due to air resistance, and because the influence is non-linear, that ideal starting angle to reach the maximum distance will always be slightly below 45 degrees, but the exact value depends on the initial velocity, the shape of our object and so on. One last animation for a different test. Here we launch our baseball while we are already up in the air. We launch at random directions all around, as you can see. We do that to test if our angle of attack from the air resistance is calculated correctly, and it looks to be the case because of the symmetry that we can see in the results. With this animation I can also demonstrate what I mentioned previously, which leads to an incorrect result in the simulation, and we take a look at what happens if you do so later in the video. If we now run the same animation but using the wrong implementation, We now put the result of the previous correct simulation on top. I think it is obvious that some of our trajectories are no longer correct. You would not see this difference in the first two simulations we've made, because the effect does not matter there. But here it does. The takeaway of this should be: it can be tricky to validate a simulation, and even if it looks correct at first, there's always a chance that some detail is not quite right. Debugging for issues like this is something you have to learn by doing it over and over, figuring out where problems are and fixing them. Alright, thank you for making it to the end of the video. I hope it was interesting to watch, you have learned something, and you are now eager to write some simulations yourself. The next video will be another simulation example, and in the video after that we will finally cover the ODE for 5 integrator. Other than that, like, share, subscribe. Thank you for watching, and I will see you in the next one.